We have seen that with the previous design, minimal settling time control, we could have cases where the control energy is oscillating. We would like to impose restrictions so that this becomes impossible. So we have to kind of make sure that at some stage the controller output becomes constant. And using this restriction leads to the so-called deadbeat controller. Well, it is not possible to use deadbeat control for any type of system. And to see this, assume that we want to follow a reference signal that is polynomial in MR. This means that at the output of the process, we have an output that is growing as t to the power MR. And at some stage we have said we want the input to attain its final steady state value. So with a constant input we have to produce something that is growing as a power of t with, and this exponent here is MR. Well, it's the type of signal that we want to follow. Remember that it's usually MR is equal to 0, a step signal, or MR is equal to 1, a ramp signal. But you can see here that if you want to produce that type of signal with a constant at the input, well, then you need at least MR pure integrators in the process. So we need LP larger or equal to MR. So with our process, that is 1 over STS plus 1. Well, we have one integrator in the system. This means that we can, well, implement deadbeat control with MR is equal to 0 and MR is equal to 1. We'll come back to that. So since we have at some stage the continuous time control output that attains its steady state value, right? And well, that the output will be polynomial in MR, just as we request for our reference signal, it means that the deadbeat controller will also attain its steady state output in a finite number of samples. We have seen that deadbeat control imposes the output to become constant after some settling time, and well, in this case it means that we can write the Z transform of the controller output as follows. Well, it's a finite sum of shifted steps. Let's take an example of that. So what I will draw is a typical controller output that will settle after some time. So this is K over here, this is XK. So we have 1, 2, 3, 4. We'll have the levels 1, 2 and 0.5. And for instance, the controller output could look like this. So it goes to 1, then it stays 1, then it goes to 2, and then it takes its final value at 3. Right? So if we have to describe this in the time domain, we have xk. Well, here we have a step input, so u of k. We have an additional step in 2 that will take me to the value 2. So we have uk minus 2. In 3, well, we have to subtract 0.5. Right, and then we're finished because the output takes its final value. If we now go to the Z domain, we have x of z is, well, 1 over 1 minus z minus 1 plus z minus 2 over 1 minus z minus 1 minus 0.5 z minus 3 over 1 minus z minus 1. So this is clearly of this type, and we can rewrite it as 1 minus, plus z minus 2 minus 0.5 z minus 3 over 1 minus z minus 1, and this one here is xq of z, the one that we have over here. So indeed, the controller output becomes constant after some settling time, and we can write its z transform in this form where x of q is a polynomial in z minus 1. What we'll do is what we have done previously for minimum settling time control. We'll kind of describe the process in such a fashion. Remember that for the denominator we have to consider the poles on the unit circle and treat them separately so that they are not included in a minus z. So we treat the integrators separately. Here LP is the number of integrators. Well, we can now write the output of the process in two ways. This is simply writing that while it is p of z times the input, and we have imposed the input to be like this because we want the controller output to attain its steady state value in a finite number of steps. And this is simply writing that it is t desired r of z. So this is the step response in closed loop that we desire, and of course those two expressions should give you the same thing, right? The same y. So what we can now do is equate this and isolate xq of z, and remember that xq of z is a polynomial in z minus 1, right? We equate, we isolate xq of z, and this is what we obtain. Of course, we can rewrite this because we have integrators in the numerator and denominator. This is what you obtain, and you can clearly see that in order to impose that xq is polynomial in z minus 1, well, this is also imposing that x is going to attain its steady state value in a finite number of steps. Well, in order to impose that, well, you see here that t desired must be constructed as b plus times b minus times some polynomial L of z, right? And in this way, well, these ones will disappear and you'll end up with a polynomial in z minus 1. This means here, and this is the difference with minimum settling time control, that all zeros of the process, both the ones that are outside the unit circle and the ones that are in the unit circle, are kept in the polynomial, desired polynomial in closed loop t desired. So in this slide we bring everything together. Remember that the process is b plus b minus at the numerator, and at the denominator we have a plus a minus and then a number of integrators, right? Well, the controller is designed in such a way that we have the following behavior in closed loop, and this is here a polynomial in z minus 1. Remember that we have imposed that pc over 1 plus pc is equal to t desired. So this will lead to 1 over p, right, times t desired over 1 minus t desired, and in our case this will be a plus a minus then this number of integrators here, LP, T desired, and then we have B plus Z, B minus Z, and then we have 1 minus T desired Z. Okay, so what we have to do is to make sure that there are no unstable pole zero cancellations. Okay, so what you could cancel over here is this one. Okay, but this is not a problem since you have included it in the desired polynomial. So in here the B minus will disappear from the controller. Another pole zero cancellation that you might have is this one here, the unstable poles with the numerator of the controller. So what you have to do, and the same thing with the integrators over here, with the integrators in the process. So what you have to do is to include them in the polynomial 1 minus T desired. So it's this number of integrators times a minus, right? So you can write it like this. It's 1 minus Z minus 1 LP a minus Z, right? This will make sure that this disappears from the controller, and then you have to put a number of integrators in your controller, LC, and this LC depends on the steady state accuracy. Okay, what kind of reference signal you want to follow and what kind of, well, disturbance you want to be able to reject, and then times some polynomial kz, right? And this is what you obtain. So adding these two equations over here leads to the Diophantine equation that is over here. And if you compare with the one that is associated to minimum settling time control, the difference lies over here, right? We have kept B plus in our desired closed loop polynomial. So the controller is 1 over P T desired over 1 minus T desired. If you plug everything in, T desired and 1 minus T desired, and you do all the simplifications, this one over here, this one over here, the A minus, right? You end up with this controller, and this is the deadbeat controller where L and K are the solution of this Diophantine equation. So another thing that we have to stress is that since we have kept B plus in the desired closed loop polynomial, well, this has implications on the Diophantine equation, right? This is this one, but you can see now that in the controller, and I didn't show it previously, well, also the B plus is cancelling out. So you can see here in this controller that the B plus has disappeared. So this is another difference with the controller that is associated to minimum settling time control. And this will make sure that in our tutorial example where we have this 0 of the process that is close to d is equal to -1 will not be cancelled in the controller, and in this way will not have this oscillating behavior. This is normal because with deadbeat control we have imposed that the controller output should settle after some time. So let us apply deadbeat control to our tutorial process that is given over here, where the time constant is 10 seconds and we want a sampling interval that is 1 second. Well, deadbeat control is a direct digital design method, so we need to base it on the zero order hold equivalent description of the process that is given over here. This is what we have computed a few slides ago, so quite a few slides ago. We have to bring this description of the process under this form. Okay, this is this factorization of the numerator and denominator under this form. And here we see that the number of integrators is 1, so we have one pure integrator in the system. You see it over here and you see it over here. Okay, so here you see clearly that LP is equal to 1. So for deadbeat control, we had that LP had to be larger or equal to MR. Okay, so LP is equal to 1 here, right? LP is equal to 1. So this means that we can obtain a deadbeat controller that is able to follow a step. This is MR is equal to 0, or that is able to follow a ramp. This is MR is equal to 1. So let us continue, and in this case we want to be able to track a step input. This means that we want it to able to follow it with a 0 steady state error. We had seen here that you need a number of integrators in the controller, that is this expression. We have 1 in the process, MR is equal to 0, so we need 0 integrators in the system. Indeed, since we want to follow a step input and we have already a integrator in the process, we do not need to put one in the controller. This means that we'll be able to track a step input, but we won't be able to track a ramp input. So this is the Dafontaine equation that we have to solve, and if we inject everything and LC is equal to 0, this is the Dafontaine equation that we have to solve with a K that is given like this and an L that is given like this. So if you write this Dafontaine equation, what you'll have is 1 plus K1 Z minus 1 plus, oh, not plus, minus Z minus 1 minus K1 Z minus 2, right? Plus, this one is L0, so plus L0 A Z minus 1 plus L0 B Z minus 2 is equal to 1. So this one will disappear, and we can now have a look at the equations. So in Z minus 1, what we'll have is K1 minus 1 plus L0A is equal to 0. And if we look at the terms in Z minus 2, we'll have, well, L0B minus K1 is equal to 0, right? So K1 is equal to L0B. This is what we have over here. We have to inject it in this equation over here, so we'll have L0 A plus B minus 1 is equal to 0, so L0 is equal to 1 over A plus B. This is what you see over here, right? So the resulting controller is this one, where we replace LZ and KZ by their expression. So this is what you obtain. L0 is given here, K1 is given here. And as you can see here, this controller cancels the slow pole of the process. Okay, this is the slow pole. We'll come back to that when we'll have a look at load disturbance rejection. Let us come back to the choice of KZ over here. We have seen that epsilon z, and epsilon z is the z transform of epsilon k, that is the set point signal or reference signal minus the controlled output. And we had seen that we could write it as kz a minus z and then r of z. Since mr is equal to 0, this one is 1 over here, this one is 1 as well, as you can see over here. So epsilon z is kz. You can choose kz in order to shape the closed loop response, but what we have done here is choose the kz of minimal degree in the variable z minus 1, and then, well, you have to choose LZ in consequence to find a solution of the Diophantine equation, and this leads to this design. What you could do is take a higher order polynomial kz to shape the response in a different fashion, right? But this will become a little bit more difficult then. So let us look at the Matlab code. This is really obtaining the zero order hold equivalent description of the process. Here we do the implementation of the deadbeat controller with LC is equal to 0. This is obtaining the two relevant transfer functions, and what we do now is compute the step responses. Okay, so this is obtaining the output. This is obtaining the control energy, and this is new. We kind of obtain also the ramp responses, and there is no command ramp. So what you have to do is use the command lsim, right? You could also use a step response and include an additional integrator in the process. That would work as well. What you see here is the closed loop output response, and this is obtained using the Matlab code. So using the Matlab code, you can see what happens at the sampling instance, right? And using Simulink, we have obtained the, well, inter-sample behavior, and you can see indeed that the output attains the steady state in 2 sample instance. This is the associated control energy at the sampling instance, and you can see that it is rather nervous. It goes to a high value and then to an almost corresponding value, but negative. So this is sometimes called bank control. You can see that the control energy comes to steady state after 2 sampling instance, and of course here this steady state is 0, right? Since we have to produce at the output a constant signal and that you have an integrator in the process, this is kind of obvious. So this is the closed loop ramp response. Again, the curves in blue and in green can be obtained using Matlab. They will only give you the response at the sampling instance, and what we have added here is the inter-sample behavior, and well, the red line comes from a Simulink simulation, and you can see here that we are not able to track a ramp signal. We are able to follow it but not track, and this is kind of obvious because in the loop gain LZ we have only one integrator, and to track a ramp response we need 2. Since we have LP is equal to 1, we need LC is equal to 1 to track a ramp response, and we'll design such a controller later. This is the corresponding control energy only at the sampling instance, so this comes from Matlab. You can see here that again this control energy settles after 2 samples, and now it settles to a constant value. This is kind of obvious because we have one integrator in the system. The output is growing, right, linearly. So at the input we need a constant non-zero signal. Well, we can also look at the load disturbance. So what you see over here, and the Matlab code is not given, so you'll have to kind of think and see how you could do this kind of simulation, but of course you'll have to consider the transfer function in closed loop that is associated to a load disturbance. So the three first curves are again obtained using Matlab, and the fourth one, intersample behavior, is obtained using a Simulink simulation, right? So here you see first the step response that we've seen previously, and at time is equal to 5, so after 5 sampling instance, because TS is equal to 1 second over here, we have a load disturbance, and you can see, well, that the controller is not able to reject this load disturbance, and this should not come as a surprise. If it does, you should go and have a look at section 5 and the subsection on steady state accuracy. For load disturbance, what is important is the number of integrators in the controller. Here LC is equal to 0, so we are not able to reject a step load disturbance. To be able to reject a step load disturbance, we have to put one integrator in the loop, and this is what we'll do in the next design. Well, this is the control energy that is associated to this load disturbance response. Again, this is in Matlab because we have the control energy only at the sampling instance, and you can see here that, well, the output of the controller stabilizes to -1. Okay, this is to compensate the load disturbance that is 1. So the sum will be 0. This is what the process will see, an input that is 0, and of course the output will stabilize to a constant signal, and this is what we observe. This constant signal is 0 over here because, well, the controller is not able to reject the load disturbance. Well, let us do this second design with LC is equal to 1. So we put an integrator in the controller, and in this way we'll be able to track a ramp input, but we'll also be able to reject a step-like load disturbance. Okay, this has been discussed before, and in order to understand this, you really need to master what has been said in section 5 in this subsection on steady state accuracy. So the Diophantine equation is still the same, right? LP is equal to 1, but now LC is equal to 1 because we put an integrator in the controller. So we obtain a different Diophantine equation because we have a square over here. We'll still take the same K of Z, right? But this will have an influence on the LZ, so we need to take an LZ that is first order in Z minus 1 in order to find a solution. I will not go through the calculations, but this is the solution of this Diophantine equation. You can solve it by hand. All you need to do is write this equation and then equate all powers of Z minus 1, and this will lead to this solution. What you could do also is obtain the solution in Matlab, right? So we'll obtain the following controller, and the difference of course is now that you have here an integrator in the controller, and of course that you have this power of Z minus 1 that is appearing, and of course the values of the L0 and K1 are different because now they are the solution of this different Diophantine equation. So this is the Matlab code, and well, the only difference lies in the type of discrete time deadbeat controller that is implemented. Here we have one that corresponds to LC is equal to 1, and this is the integrator that you have in the controller. This is the closed loop output response. Again, in blue and in green, this is what you obtain using Matlab. You have the response at the sampling instance, and the intersample behavior is obtained using Simulink. You can see now that the steady state is attained after 3 seconds, so 3 sampling instance. Again, we have TS is equal to 1 second over here. You can see here that the presence of this additional integrator in the controller, that is not necessary to follow a step response, but that we have introduced here to follow a ramp response, or to be able to reject a load disturbance, a step-like load disturbance, well, has had consequences on the closed loop step response, because it has become a lot more, well, problematic in the sense that the overshoot is very large. This is the control energy at the sampling instance obtained using Matlab. So again, we see that the control energy settles after 3 sampling instance. It settles to a value of 0. Since we have one integrator in the system, this will ensure that the output settles to the constant value 1 in this case, since the set point is a unit step. So this is the output ramp response. Again, in blue and green, this is what you obtain using Matlab at the sampling instance, and the intersample behavior is obtained using Simulink, right? So you can see now that the presence of this integrator in the controller, so we have now 2 integrators in the loop, one coming from the controller and one coming from the process, has allowed us to follow and track a ramp response. This is the control energy at the sampling instance coming from a Matlab simulation. You can see that the controller output settles after 3 seconds, so 3 sampling instance. You can also see, as is usual with this deadbeat control, that you have this bang bang type of control, so this very nervous control. Well, the controller settles to a constant value. This is normal because the output is climbing linearly. Okay, so since we have an integrator in the process, we need at the input of the process or the output of the controller something that is constant, and this is indeed what we see. We can now have a look at a load step disturbance. So again, here the code, the Matlab code to do this is not given. You'll have to think and see how you can do it yourself, but the 3 first curves are coming from a Matlab simulation, or could be coming from a Matlab simulation, because you see that you have the information at the sampling instance. The red curve, so the intersample behavior, is of course coming from a Simulink simulation. So here you see the set point closed loop step response, and as you can see, the system will kind of settles after 3 samples, and after 5 seconds, so 5 sampling instance, we do a step-like load disturbance. And this time, since we have an integrator in the controller, you can see that, well, the output returns to the set point, although you can see here that this conversion is very, very slow, and this is because we have cancelled the slow pole in our design. Remember that C of Z, well, you had a denominator, you had part of the numerator that was 1 minus exponential of minus ts over tz minus 1, and then the rest, right? So this is cancelling the slope pole of the system, and as we have discussed before, this is not a good idea if you want to have a good step like load disturbance. Because of this cancellation, well, this load disturbance has become very slow. This is again the control energy coming from a Matlab simulation, as you see it only at the sampling instance. And here you can see here that, well, the output of the controller settles to -1 to compensate for the load disturbance, as well we have one integrator in the system and the output settles to a constant signal. The output of the controller plus the load disturbance must go to 0, and this is indeed the case. Notice also this very nervous control, right? And this is kind of the signature of deadbeat control. You have this kind of bang bang control that is rather nervous. This concludes this section on deadbeat control. As you can see, the deadbeat controller produces a nervous bang bang type control. So the deadbeat controller is not suited for any process. There can also be issues with robustness. So robustness is what happens if the process is a bit different to the model that you have used to design your deadbeat controller. Deadbeat control is something that you can investigate in your laboratory assignment that is associated to this theoretical course. So you could, for instance, apply it on the actual LTR 700 system, this airstream and temperature control system.